So today we move beyond lines and we begin to cover new ground. Instead of integrating over lines, we will begin integrating over two-dimensional objects. In this case, in the lecture today, rectangles, but in the future lectures, we'll move to integrating over general two-dimensional surfaces, moving beyond our one-dimensional lines. So let's first recall some basic results from Calculus 1. And the problem we want to recall first is this area problem. This is how we will set up the idea of a double integral. So first let's recall this original idea that led to the development of much of calculus, integral calculus, was the area problem. Given a curve, f of x, how do we calculate the area underneath the curve? And as you should well remember from Calculus 1, the way to find this is the Riemann sum approach, where we divide the interval from a to b into small pieces of width delta x. Then for each slice I can be any number between 1 and n, the number of slices. So for each slice I, estimate the contribution to the area for that slice. And you can take a pretty simple approach. You just pick a value of f of x within the slice and choose f of that value. That would be your f of xi. And then that's the height, and multiply that by delta x, that's the width, and that gives you a small amount of area. And then we just add all those areas up. We add them all, I forgot a summation sign here. Add up over all of the i's, all the areas, and then take the limit as delta x goes to 0. And you saw different ways to do this. You could construct rectangles on the left-hand side, which I've drawn here, or rectangles on the right-hand side, or the midpoint rule, or the trapezoidal rule, various things like that for ways to estimate the area within a slice. But this is the basic idea. It's a three-step process. You slice the domain into pieces, you estimate the contribution from each piece, and then you sum them up and take the limit, and that is what we denote the integral. Okay, so this notation here is nothing more than a shorthand notation for this limit definition of the integral. So now let's move to a more general problem. Let's generalize that problem to a harder one, but related. Given a function, and now a two-dimensional function, z is a function of x and y, that creates a surface above the xy plane. And we might ask, what is the volume under that surface between the xy plane and that surface within this rectangle, where x may go from some number a, here drawn to be 0, to some number b, and y may go from some number c, again here drawn to be 0, to some other number d. So it's the same kind of problem, right? We have some function, and we have the distance between either the xy plane instead of just the x-axis, and we need to add all these things up. In fact, if you were just to look at the x-axis alone, there would be an area here associated with this left-hand side of this object, and that area would be a one-dimensional integral. And so we're asking some more general but very related question. So the way we answer this question, again, is to go back to basics, Riemann sum kind of basics, and construct a limit definition. So we take the domain, and we divide it into squares, assuming we have some rectangular domain from a to b in x and from c to d in y. We cut that into little squares, and here's one square. Then we go over here to the function, and we project that square up onto the surface, and we get some little piece of the surface. And we say, okay, this is about equal to a rectangular prism. How tall is this object? So we pick any point on the inside, and we say, okay, that's how high we're going to call this square. I'm getting a little ahead of myself. Here we just first divide the domain into squares. Here's our square. Here's what the function looks like above that square. Then we estimate the volume within that little piece. We say pick a point inside the square, call it xi, yj. There are I rows and j columns of squares. And let's take f of that value and call that approximately equal to the height. And then delta x, delta y are now the area of the square. So we cut the domain into squares of size delta x and delta y, and that gives us small rectangles within the domain. We then multiply the area of that base times the height, approximate height of the object, and that gives us the approximate contribution from that little slice. Finally, we construct a Riemann sum. It's now going to be a double sum. We have to sum over all of the slices in the x direction. That would be the sum over I for xi. And then all of the slices in the y direction. So we sum over j for yj, and then put them all together. So that's a double sum of the values of the function in each little rectangle times the area of each rectangle. We then take a limit as x goes to 0 and y goes to 0. It's no longer sufficient just to let one or the other go to 0 in order to make this thing accurate and become no longer approximately equal, but rather truly equal. We need to take limits in both x and y. So we do that, and then we say, here I have something that looks like the first part of a single integral, except I have two of them. I'll denote that with a double integral sign. Here I have an integrand, and this delta x, delta y, that's the area of each rectangle getting smaller and smaller, and so we'll call, this could be called delta A if you like. So we'll take that and replace it with dA. And we get the double integral. So the Riemann sum, the summation and the limits get replaced with the integral. The small rectangles get replaced with dA, and the function remains unchanged, f of x and y. And we call this object a double integral. So conceptually, just to review, the integrals are the sum of over all the squares, f is the height within each square, and dA is the area of the base. Base times height is volume. And that gives us the volume. So this is how we define the volume under a curve. So that's fine. We have this nice notation. We have this Riemann sum, this notation, but how do we actually find these numbers? Okay, the problems in the book will be numbers, calculate the number. And so how do we find them? So that's going to take a little more thought. Let's look again at this Riemann sum. I've just rewritten it from a previous page. It's the limit as delta x goes to 0 times the limit as delta y goes to 0. Sum over all the x slices, sum over all the y slices, times the height function, times the delta x, delta y. So I have all these pieces. These pieces are all multiplied together, and I'm taking four operations here. Sum over j, sum over I, limit as delta y goes to 0, and limit as delta x goes to 0. Now, there are specific criteria that allow you to interchange these different operations. Sums, limits, limits with each other, sums with each other. And they usually boil down to the function being smooth enough. If the function is smooth, and that's what we're pretty much always going to assume in this class, in fact always, as long as the function is sufficiently smooth, then you can interchange limits and sums, and you can interchange sums and limits and limits. So you can mix these things around however you want. Basically, any function that describes a truly physical situation is probably going to be smooth enough to you do these operations. And this class will not consider sort of pathological cases where you can't do that. So, assuming that we're free to rearrange these things, let's go ahead and do so. We have here limit delta x goes to 0, delta y goes to 0. But let's take this sum here, which is a sum over I, and I is associated with x, and let's put it next to the limit of delta x going to 0. Okay, so this will go over here and change places with this limit here. All right, now what we have is limit delta x goes to 0, sum over all the x slices, times limit of delta y going to 0, sum over all the y slices, of f of x, and I've interchanged these two as well, delta y, delta x. And now I can begin to make things pop out at me by using parentheses. So I've drawn here parentheses around the function itself. This is somehow like the inside. We'll start here, f of x and y. The next set of parentheses goes here to the left of limit delta y going to 0 and to the right of delta y. And finally, limit of x, delta x going to 0 and delta x. So this here is the standard definition of an integral over y. Okay? It doesn't say anything about x, this limit delta y goes to 0, sum over all the y slices times delta y. That doesn't say anything at all about x. And so within this process here, inside the blue parentheses, x is treated as a constant. And then we have a second process, which is done over x. Within the first process, notably that integral y will be eliminated if it's a definite integral, and so the remainder inside the blue parentheses will only be a function of x, which was treated as a constant. and then we integrate over x. And so what we see is that this structure says you can do them sequentially. Do the y integral first, then do the x integral. Or, and that's what I've written here. Sorry, that was not very well done. F, do the y integral, then do the x integral. Or, we could have rearranged things differently. We could have pulled the limit delta y going to 0 out to the far left, then the sum over j, then the limit delta x, then the sum over I, then f, then delta x, delta y. This is just a different rearrangement of all the terms in the first thing. Now we have an integral over x holding y constant, followed by an integral over y holding x constant. I mean, x will have already been eliminated, so followed by an integral over y. So what we've seen is that you can do this either way. You can do the integral in x first, or y first, and then y, or you can do the integral in y first and then x. So this is just another way of looking at that. Given an integral of f over some region of space, dA, we can first do the y integral from c to d, the bounds on y goes from c to d. We do that integral. That's going to give us some function of x. Y will be eliminated in the integration. That'll be some function of x, and we can integrate that function of x from a to b, getting the antiderivative of capital H of little h evaluated at b and a. And this function little h, which comes about from integrating f once with respect to y, that's like the area of a slice in the y direction. If I fix x, then when I integrate over y, that's like integrating this area here underneath this curve at this value of x that I have fixed. So this is just the one-dimensional area function as a function of x, and then I add up those areas to get volumes. If I do it the other way, I turn this double integral into an integral first over x and then over y. That's like first picking a value of y, a constant value of y, and integrating over x, which will give me the area of a slice in the x direction. Sorry, that's incorrect. Slice in the x variable. Okay, and then we'll call that g of y. And then we integrate those areas to get a volume. So I can slice in x, get areas, integrate to get volumes, or I can slice in y, fix y to get areas and integrate to get volumes. So based on these alternate geometrical definitions, and also based on the Riemann sum definition, we seem to be seeing the fact that these answers should be equal. And in fact they are, and this is called Fubini's theorem. We won't say much about it. So to summarize, double integrals can be found from Riemann sums. They can be evaluated sequentially. In general, we're allowed to change the order of integration. We can do whichever one we like first, although there will be caveats to that later on. And the final thing to remember is that when I'm doing one integral, I have to remember to hold all my other variables constant. Okay, this is just like partial derivatives. When I'm taking a derivative with respect to one variable, every other variable is constant. The same is true of integrals. When I'm integrating with respect to x, y is held constant. Conversely, when I'm integrating with respect to y, x is held constant. We'll do just one example to keep this video from getting too long. There are many, many more examples, and we'll do many of them in class. But a simple example which illustrates the fact that you get the same answer both ways. So here we have the integral of xy, the function xy, in x and y. And the way that you figure out what the limits are is you work your way inside out. So x goes from 2 to 3, and y goes from 1 to 2. And these things should go from inside out. Okay, so whatever your y limits are, if your integrals go x, y, z, or in this case x, y, then your d it should be dy dx. Here it's implied that we're going integral over y, integral over x, and so then we work our way back out dx dy. In any case, let's do it. Integral from 0 to 1 dy of the inside. Integral from 2 to 3 of xy dx. We do that, we find that antiderivative. We hold y as a constant. The antiderivative of x is 1/2 x squared. So xy, when integrated in x, becomes 1/2 x squared y. Evaluated from x equals 2 to x equals 3. All right, we plug those in. When we plug in x equals 3, we get 9 halves y minus 4 halves y. That gives me 5 halves y dy. This is now just a plain old single integral. That's 5/4 y squared. Y equals 0, y equals 1. And we just plug in the 1, we get 5/4. I could have done it the other way. I could have said, first, integrate in y, then integrate in x. So if I write it that way, I integrate in y, I get 1/2 xy squared. The antiderivative of y is 1/2 y squared. X is held constant. I evaluate from 0 to 1. When it's 0, I get nothing, so I plug in the 1. That gives me 1/2 x dx, integrated from 2 to 3, which again is 1/4 x squared this time. But I now evaluate from 2 to 3, and I get 9/4 minus 4/4 is 5/4. So I do get the same answer both ways, as I should. And we'll do many, many more examples in class. After a good deal of practice, this will become second nature, and so we just have to do the practicing now.